3 key lessons in application server optimization, November 15th, 2023, hot off the presses. Weeks I've spent most of my time, weeks. I spent most of my time improving the performance of, wait, something's wrong here. Something's wrong here. Something's wrong here. I zoomed in and it got all effed up. Oh yeah, it got all effed up once you zoom in. Okay. Over the past 6 weeks, I've spent most of my time improving the performance of Graphite's application server, affectionately nicknamed Subwoofer. While this effort is still fresh in my mind, I wanted to share 3 key lessons that help us find meaningful performance gains, and in doing so, greatly improve the Graphite user experience. Okay, I'm pretty excited about this. Yeah. By the way, I do love it that I want to be able to zoom in and have all the side stuff go away, so I can just look at the article, because now it has to be so small. You know what I mean? It has to be so small. All right, context. We started to investigate our app server performance in earnest after noticing a few concerning trends in the data over the summer. Okay. At the time, we would semi-frequently experience large but unexplained regressions in server endpoint latency. All right, every 3 or 4 weeks, a team would get paged because a large regression in endpoint response time. Think something like P90 shifted up to 8 seconds for a few minutes. Oh, that's crazy. If you're getting 8 seconds on a P90, that means 10% of your customers are having 10 or 8 seconds or larger request times. That's crazy. I smell GC issues? I don't think so. You'd have to be on an old-ass version of Node. You'd have to be on, like, Node 12. In practice, these regressions would render the Graphite's dashboard unusually slow for reviewing or merging PRs. But then again, really large amounts of React can be quite slow. Despite day-long investigations into these regressions, each time they cropped up, the cause of these incidents remained a mystery, heavy profiled. As a result, we began settling into an uneasy rhythm that we've noticed large performance regressions scale up the number of server pods, dig in, usually find nothing, and just move on, repeating the exercise again for a few weeks later. Really, being able to run a server, isolate a server, run it to the ground, profile. Usually if you're on a server, perf utilities around, perf's a great one to really get a good look at kind of where time in generally is being spent. Between the aforementioned regressions and the outlier users we've noticed we're adding disproportional load, our site performance graph were extremely spiky. When teammates and or users in our Slack community remarked that our site had gotten slower over the past window of time, it was difficult to authoritatively verify or disprove this, let alone pinpoint the cause. Wait, what? Of course you can verify it. You just effing said your P90 was above 8 seconds. You can verifiably verify, yes, with all authority, we're slow. Right now, we're slower than we were, and it happens a lot of times. We don't know why. Sorry, my P90 69 is under 3 milliseconds. Well, damn, son. That's fast. Anyways, that's kind of, I feel like you can verify that these things are happening. It's just why we have no idea. There was a clear user pain to be addressed. If only we could get wrangle on the system. Yeah, okay. The hope for this investigation was 2-part. Learn where those large regressions were coming from and remove any of them as possible, reducing the bad user experience and making it easier to understand app server performance trends over time. Let's dive in. Typically, I'm just gonna toss out before I look. It almost always come down to copying promises. React server rendering. Just gonna throw it out there. Your P90 is 5.7, almost statistically average. I'm just gonna assume the problem isn't with looking up data. Maybe that's gonna be 500 milliseconds. But that's usually a very obvious problem when your database is the slow thing, okay? All right, throughout this investigation, I used our existing P95 server endpoint metric as my guide. Whenever I saw a spike in this metric, I would dig in, as opposed to past incidents where we would investigate things would return to normal, and then we'd move back onto other work. This time, I didn't rest until I had answers. We had a hypothesis, of course, but the results were actually surprising. A few things emerged. Okay, 101, verify the underlying impact. P95 latency can be too blunt. Okay, interesting. Okay, what does this mean? This lesson is key for an application that integrates with a third-party API, in our case, GitHub's. In the case of such integration, it is possible for an upstream third-party API provider experiencing an incident to spike your app's P95 response time. Okay, that's fair. This is fair. You should put timeouts. Always put timeouts. All without any real degradation on your side. During the 6 weeks when I was working on performance, a large customer onboarded onto our Graphite. Yeah, I don't know what Graphite. I don't think I've used Graphite. A few days after the customer onboarded sessions, we've noticed a surge in server latencies. Okay, so we're having some issues. Hi, QPS, failing server nodes, DB bottlenecks. Okay, exciting. Graphite is awesome. Time series database. Oh, super cool. I've never played with the time series database. I always have to use Hadoop at work. Or Hive. A lot of hiving. Told ya. And so I've never played. I've briefly seen Grafana, and I almost had to write an adapter for Grafana, but I've never played with Grafana much. So, looking at a rollup on the top user endpoint combinations, we noticed that a surge in the number of requests was coming from a specific set of users. When one of these users would try to load the insights page on the Graphite dashboard, our app server would try to grab a profile info for every GitHub user in their mono repo, including their GitHub avatar URLs, which needed to be proxied through a server, resulting in a single network request for each avatar and thousands of requests with a span of seconds. This was not ideal, but easily remedied. Okay, great. Great stuff right here. Don't make 1,000 requests, okay? I just assumed that whatever the problems were, we weren't going to see these type of problems because these are very obvious problems. Don't make 1,000 requests, right? Like, that's just bad. It's just bad for business, okay? It creates 1,000 promises. It has to wait for 1,000 things to be done. It's just not a good thing. We quickly stemmed the bleeding for this customer, and based on the knowledge we had around queries per second, the cost of each request assumed that we had taken a site-wide hit in performance because of the spikes in overall server latency. However, digging in showed a different picture. Our server actually processed the thousands of avatar proxies with no trouble. Instead, it was the customer GitHub enterprise instance that had become overwhelmed, leading to a high endpoint latency for this particular organization, but perfectly normal behavior for all other Graphite users. Okay. The lesson here, sometimes P95 latency can be a bit too blunt and shift as a result of a few outliers. I don't get that. I honestly don't get that phrase because I'm just trying to understand it. P95 means your top 5% of your customers. It's not a few outliers. It's the 4.99% behind the P95 that are slower, right? So if you see a shift in your P95, that means there's, like, people are hurting, right? 5%, 1 out of 20. If top 5% is 5 users, then it's an outlier. Well, if top 5% is 5 users, I'd have to think about that. Okay, so the P95 is the number of requests, and you have power users in which are distributing most of the requests. So is that what they're trying to say? So that the P95 could just be a couple users? If the top 95 is 5 users, then your bottom 95 is 95 users. If you have 100 users, you don't really need percentiles, right? You want percentiles always. So that's the thing I guess I'm a little bit confused on. What does this mean? Are they saying, like, because one really good way to make sure that you're doing a good job measuring how users are affected is that you need to be able to take all of a user's experience and then take that individual user's experience and average it, and then take the medians of the user's averages. And why I think that is more important is that one user that does like 900 things becomes a singular data point. That way you have a more reasonable distribution of what is happening for each user. You can have better insights into each user. I always found that to be a way better way to kind of look at these type of things. You don't want to let one power user shift, your stuff around. Just something to think about. We've since seen other instances in which P95 latency was pushed up because of a regression. In one endpoint in particular, while I still use P95 latency as the simplest leading indicator, it's crucial to attach it to a chart of P95s grouped by endpoint. Yep, fair, good. Average users. No, you want median average. You want to do the median always. Median is good. You don't want to just do averages across the board. You only take average of the user's experience. Then you look at the quantiles of the averages. Then it's a little bit nicer. I think in the TLDR is you are a big client, so we'll ignore your bad experience. Well, yeah, not the median. You want quantiles, but you get the idea. You get the idea. All right, P95 by endpoint, very interesting. Look at that purple just blow up. Interesting. For an example, you can spot the significant jump in P95 at just before 6 a.m. above is actually due to a spike in response time from the yellow endpoint. I honestly can't tell. I mean, I see these spikes in yellow, but I also see spikes in purple. Blue has been really spiky. I can't quite tell what he means by that. Now, this, on the other hand, this chart. Yes, this chart seems very reasonable to look at. This chart, I can really see that things were happening, and then all the things seem to happen. But still, I'm not sure how. I don't really know what's happening because blue is low, and then blue just skyrockets. But yellow's been up for a while, been up for 8-10 hours. On the other hand, here's a clear example on Thursday, July 24th, where there is a true site-wide regression with all the lines spiking each other. Let's see, each color representing a different endpoint. Okay. I still don't really understand. I don't quite understand the lesson here. I don't understand the lesson. I just think they're not necessarily measuring their P95 potentially well. Unsure. Watch out for the event loop blockers, in particular big queries. Okay, I like this. This is good. With the per endpoint graphs in place, I started honing in on the use cases where we'd see site-wide regressions and a surge across many endpoints latencies simultaneously. Some of the regressions were the result of issues we were familiar with: high database CPU, an outlier number of requests, servers running out of memory. Classic JavaScript on that last one. I love that last one. That's not a skill issue. That's just a JS issue and sort of a skill issue. But for the other regressions, all of our variables seem to hold at healthy levels, despite a jump in latency. In some of those cases, we just see a quiet period where everything would look healthy. Then there'd be a few or no error logs, but latency would still be sky high. Yeah, you're blocking, baby. Because of the lack of concerning external variables, our hypothesis was that there must be something occurring within Node.js process itself. Enter node event loop blockers. Oh, interesting. Is there a specific list of event loop blockers? Don't block the event loop or worker pool. Well, yeah, but who's blocking? I mean, sometimes you have to do a lot of work. I mean, that's just a reality, and that blocks. The simple mental model here is that Node is single-threaded, so when you do heavy synchronous compute, you can block the process and thus the server from handling any other in-flight requests. Yes, Datadog provides a basic out-of-the-box dashboard here, though granted, it does have some weaknesses. It also slows everything else you're doing down. So if you're having problems with promises / like crushing out stuff, you also, by the nature of observing, make things difficult. Namely, that once you get down to this service level, you can't slice on a per pod basis, despite each pod having its separate node process with its own event loop. You can't examine each pod granularly. Oh, that's too bad. I assume they can fix that. That seems like a fixable issue here. This means that a large event loop blockers may get hidden and averaged out if the other 9 server pods at the time are doing fine. You could also just, if you're just doing testing, you could also just launch a bunch of single pod instances out there, right? I mean, yeah, you're being really wasteful with your CPU, but for a little while, be wasteful to try to catch a problem. I think that's fair. Instead, I suggested via Ashby in an extremely helpful blog post, I found logging to be a more fruitful approach. I do like a good old-fashioned logging. As a side note, we also tried profiling our CPU using Linux perf tools as per Netflix suggested. Let's go! Is this the Unong one? I like this one, but we wound up preferring Ashby's approach for a couple reasons. AWS doesn't expose the underlying settings needed to use Linux perf tools on ECS containers. Oh, okay. Okay, fair. Ashby's approach allows us to identify the specific requests that block the event loop, making it easy to replay said request with the exact details to recreate the blocking conditions. This wouldn't be possible with plain Flamechart. Okay, that's fair. That's really fair. Here's what the end result of implementing this logging approach looked like. Oh, very cool. Okay, so you're able to replay these requests and you just put a bunch of logs in that effectively track all the logs and the time spent for each one of these. You have effectively a bunch of performance counters. and you have a bunch of things summing it up, and then you have the related request coming in. That's pretty cool. The APM trace includes request start log, which allows us to replay the request locally with the manage command that then spits out an associated curl command to replay the request and debug against a local server. Very cool. That's super cool. After debugging lots of requests in this manner, there are a few common themes. Half of the event loops blockers were from intensive synchronous work that we were doing, rendering React. In this case, we moved computation off the main event loop and into a worker thread. The other half came from database queries, specifically database queries that returned a significant amount of data. When type ORM received results back from the database, it parses these raw results and transforms them into typed entities that we then interact with in our code base. Or are they using, is it some sort of input validation like Zod? SSR is not bad. Some SSR is bad. Not all SSR is created equally. Let's see. Because I'm curious about this, because when it says that you have a typed ORM, is there some sort of like Zod-like validation for this? Because Zod is like definitely not known for its speediness. Now, maybe it's gotten better. I haven't looked at it in a while, but Zod is most certainly not fast. When these raw results are large, 3 megabytes or larger in our particular case, this parsing can be extremely expensive. Valid. I verified this by cloning a type ORM locally, plugging it into a server, and adding custom debug logs. Yes, it's blazingly... type ORM does Zod stuff, yeah. So yeah, that's very, very... Typically type validation, runtime validation, because you're not using a real typed language. Remember, TypeScript is not statically typed. It's a lint, okay? If you think of it as a lint, you will not be disappointed as much with TypeScript. But the moment you think about it like it's typed, like it's enforcing some sort of types, no, it's linting, okay? It's just letting you know when your types are out of place from each other. That's it. And so that means if you want to know you're using a real type, you have to do a runtime check on it, meaning that you have to crawl the entire object using object.keys, using whatever it takes to go through the whole thing and validate its key and its property as being the same thing. It's just different. You can't just use type of, right? Because if you want to validate an object is of a certain shape, has a few keys in it, you have to go through it all. So typically people will use type guarding as one of the better ways, but I mean, there's still a lot of oddities that goes through with type guarding. You can type guard not realizing a certain field became undefined. That's a real thing, right? You don't realize a field can be undefined from some particular third-party service or whatever, and then you get this response back out. It happens to be undefined. You didn't know about it. You blow up your server despite your TypeScript saying everything is good, great, and awesome. So, there's these weird little oddities that will show up if you don't have perfectly correct types. TypeScript just moves the problem from type checking in your code via runtime to type checking via lint. It's good. I mean, don't get me wrong. I'm fine with what they do. It just still can be difficult. It's not free, is what I'm trying to say. So this is why you run into these situations, is that you are type checking. I assume that's what type ORM is doing. It's literally type checking against your data, making sure that you've adhered to some sort of schema. All right, the results may be larger because we're querying for a large number of rows, or because the joined data in the query. Type ORM maps the joins in the entity manager to left joins with which can result in significantly inflated number of rows. Hold on. Type ORM maps the joins in its entity manager? Hold on. It's doing a left join in TypeScript? Is that what I'm seeing? Not free, called it. Pick, is that what I'm reading here, Pick? Pick, am I reading that you're doing a join in not a database? TypeORM maps its entity managers to left joins, which can result in significantly inflated number of rows if there is a lot of relations between the query data. Oh, no, it just does the joins itself? It does the join, it does these left joins somewhere, and then brings a bunch of extra stuff down, is what I'm seeing. Okay, it's probably that. This means that there were a few seemingly innocuous queries that turned out to be timing out the Postgres serialization time, not even event loop blocker related, though the concept is the same, because of all of the joined data. I'm impressed. Okay, so it is joined in the DB. Okay, so that's good. It's not doing something that I think Prisma was doing. Prisma had the Rust client doing the join itself, which, again, just a cautionary tale. Raw dog and squeal typically results in you knowing what's happening. Squeal builders are like the next level of raw dogged. Maybe it's not as raw dogged. Maybe it's a little bit, it's a medium rare. It's a medium rare squeal query, okay? Still good. You still have a lot of control, but at the end of the day, you're not crafting the query yourself. And then finally, the last level is ORMs, which mostly can be good, right? ORMs, mostly good. But sometimes you run into these odd situations, okay? So you got to know when to raw dog it, okay? Because sometimes your queries come out medium well, all right? What is ORM, to be honest? It's just like, effectively, you're mapping things to, like, classes. Just imagine, that's how I like to imagine it, is that you have a way to effectively manifest representations that you have from the database into your code. And it gives you all the nice little things around it. I think Frontend Masters does a really interesting thing. They're telling me about it, which is they have a handcrafted squeal builder which only allows specific operations for each field, meaning you can't just look up by any field in a table. It has hard-coded each field, which ones are indexed, doesn't allow you to do that. So when you want to add a new query, you have to alter this kind of squeal builder to be like, all right, I want this new query that does this. That way they have every last bit of queries very easy to represent in the system, but highly optimized in their back end, right? Because they know the exact query every single time. There's no messing around. It's very, very fast. I love those kind of approaches because it's the middle ground, right? Typically, you, the dev, you're not doing anything. But everything is still raw, but it's protected behind what feels like a query builder. So when you go, all right, I want from this table, all of a sudden you only get 3 fields you can select on. So it kind of reduces things down to what you can do. Oh, you can't even sort this table. .sort is not a method found on this table. Sorry, you may not do that, right? It makes you think in a different way, right? It's a specific problem to a specific or it's a specific solution to a specific problem, which I really like. I think that's the best way to write any really good performance or a really good application is a specific problem and a specific solution. The more specific you can go, the better. Index scan all the BBs. You always index scan all the things at all times. There are some other interesting but niche fixes, as well as some of our pattern of mapping over a list of objects to generate promises, blocking the event loop. Nice. There could be lots of objects in that list, or 2, creating promises took some non-trivial synchronous work, constructing typorem query builders. Interesting that a query builder would take non-trivial amount of synchronous work. I'm confused by that. I must not understand how building a query would take anything more than a handful of microseconds. Okay, you have a slow machine. Maybe it takes a millisecond or 2. That's hard for me to understand. This isn't a call to prematurely optimize, which, by the way, again, call out to Casey. Premature optimization is the root of all evil is a misquote. The creators would just Hoare and Knuth would say, hey, we are talking about hand rolling assembly to make it faster than C. Don't hand roll assembly to make it faster than C. Don't do that. That's stupid. But writing good code, you should do that, okay? Optimize your code. Just don't hand roll assembly. Only do that when you really need to do that, SSL. I get it that TLS, whatever it is, 1.3 or whatever it is, does do that. That's fine. I wouldn't worry about the synchronous CPU intensive type of work off the bat, but I would rather monitor it as it rolled out, knowing that this might later have to move to a worker thread. I would say that avoid promises, you'll just find just a giant win. There are also cases, however, where there was a logic I thought would be quite CPU intensive, which turned out not to be so. This is why proper logging and monitoring are crucial in a web application at scale. Absolutely, 100%. Be very wary of large volumes of data returned from databases. It turns out that this not only has an expense on the database level and sending it down to the client, but can also affect other all-in-flight requests. Yeah, absolutely. This makes perfect sense because when you JSON decode, when you walk these objects and cast them into things, when you verify or validate their shape at runtime, you 110% spend all that time synchronously in JavaScript. There is no anything else that can run. And every time you create a promise, remember, anything, however long it takes to resolve that promise constructor, everything else behind it in the event loop has to wait until that thing is done. And so it's like, it's very good to know these things exist. From this investigation, we were able to burning down a number of these event loop blockers. However, keeping an eye out on performance will continue to be required as we inevitably introduce new blockers. Absolutely. Lesson 3, everything has a cost, but only the most expensive things have impact. Classic. Completely reasonable statement that you cannot argue with. Let's see. One of the first things I dug into when I was looking at performance was background fetching that our app did. We had noticed in Datadog metrics that our server spent a lot of time evaluating these requests. By server wall time, this was a third highest endpoint, but because of requests that occurred in the background for users, we weren't sure whether this was worth optimizing. Okay, very interesting. Interesting, but if it's in Node.js, it doesn't matter that it's in the background for a user, because if it takes time, it takes resources, and if it takes resources, other services have to be slow or slowed down, right? I mean, by the very nature. We'll find out. At the time, we decided to experiment with unshipping the feature that relied on this background fetching. Curious to see the impact showed up anywhere. After unshipping, the server CPU and memory stayed at the same, and we saw a dramatic drop-off in the event loop delay. Crazy. Key takeaway here for me with much more of this performance work was that nothing comes for free, even non-user facing latency. Again, at some point you have to process it. At some point you're taking up resources. At some point it has to get in line with other things. You know what I mean? Like, of course nothing's free. I mean, this makes perfect sense, right? You either have, you vertically scale, you horizontally scale, or you get rid of it or make it better. For a while, we've theorized that some of the large unpaginated endpoints we have are costly. However, we haven't seen this show up in our top-level performance metrics. These queries don't seem to be using a disproportional amount of CPU or memory or blocking the event loop more than the other endpoints. So while we could staff a large effort to overhaul these endpoints and iron out our pagination scheme, I am not yet confident that this trade-off will be worth it. So one thing to kind of say about this, not all changes are worth it as the first line, but making things fast mean you don't have to make them faster later when more things rely on it, or at least making it good enough. Do you know what I mean? Like, as you let things that you know aren't good sit, more things grow on it, which means it's harder to detangle that mess as time goes on. You know, almost always is it a good idea to try to write the right thing first that you know is going to be as efficient as you can write it, that's not hyper ridiculously made, right? I do not like make it work, make it right, make it fast. I've never liked that phrase. I like to make it, I try to make things performance-minded first as I make the thing, right? I design my APIs around it. I think about where and how I'm allocating memory, why I'm allocating memory. Can I reuse objects? I don't first think about making the thing, because often it becomes really difficult going backwards. You know what I mean? It's difficult going backwards and then making something fast because you've made a lot of trade-offs in how you've designed it. It can be difficult. All right, capturing performance trends. After fixing many of our outliers and our latency graphs are much smoother and more consistent week over week. For example, consider the following time series graphs that show the number of requests that took greater than 5 seconds, greater than 2 seconds, greater than 1 second. The blue line shows the data from today, and the orange tracking line shows the data from the same point from the week before. Oh, nice, some week over week graphs. Okay. It looks like, wait. Is blue sucking more than orange in this situation? I don't really see much of a win here. Let me just make sure I got that blue and orange correct here. The blue line shows the data from today. Yeah, I don't know if I'm not sure if I'm seeing like huge wins all the time. It's really hard to say that there's a win. You need to do more statistical rigor on this kind of win. You know what I mean? You have to do a lot more statistical rigor on these type of things. I would never eyeball a graph. Like, eyeballing a graph only works if it's obvious. You know what I mean? Like, if it's like one graph and there's a gulf in betwixt and then another graph, you don't have to do much rigor on that one and be like, yeah, that's probably better. were like lower at all points by at least 20 milliseconds. Probably faster. But if it's like right there, I'd be careful. I mean, this just looks like an accident right here. Now when we see the performance regressions, it becomes easy to concretely identify. In the graphs below, for example, a regression around midnight immediately jumps out. Yeah, there's like that jump right there. That must be a regression. I just don't see any difference though. It looks. Oh, what do you think of these two images? They're the same. Anyways, yeah, there's no midnight either. Previously, we were using graphs to monitor latency across our entire application, but the hope is that we can now use this approach to track performance trends on key endpoints. The work continues. Through this work, we have significantly improved our ability to understand where large performance regressions on the Graphite apps are coming from and how to combat them. I do like this. You know, the per endpoint kind of identification, week over week graphs, those kind of things, they're actually super useful because when something does regress, at least you know where and when it happened. Then you can attempt to fix it. You know what I mean? At least that's good. Identification is half the problem. It is a very good thing. I like that. I do like that. Let's see. Understand how overall site performance is tracking over time. Yeah, that's also good. Historic is always really good. It's really good to know that you're slowly doing it. The hard part is that when you creep up slowly over time, you don't do larger regressions with more statistical rigor over time, because then the problem becomes over a 2-month period. Did you slowly become slower? I can fix her. Every developer, yes, this is it. While most of this work has centered around our understanding at the most extreme outliers, we're continuously hard at work continuing to drive down endpoint latencies across the board, and more importantly, locking our wins in. All in all, this investigation, the resulting fixes have greatly improved Graphite's app server performance over the last 6 weeks, and I'm confident these learnings will only help us continuing going forward. You know what I'd love to see them do? I would love to see them just simply isolate a server, be able to run some dev tools on it, and look at the performance or the performance tab and just see how much time are they spending in garbage collection, right? Like that's such an amazing thing to do, is just looking at that. Also, what node version are they on? Are they on node 16, 18, 20? Like very, very different performance characteristics. And node 16 is like intensely slower than Node 18, which is still much slower than Node 20, right? So it's like there's some real wins there that would be great to see what's going on, because I think that if you looked at garbage collection, you can also find a huge number of reasons why individual requests or a set of requests spike for a while. Anyways, the name. I like this kind of stuff. I think this stuff is great. I love that they made graphs. I love that they're tracking. Tracking is always the best first step. I love they're being proactive about it. Absolutely lovely. These graphs I don't really buy. You should really get some statistical analysis in here. At the startup, at places where I've worked, we call this automatic canary analysis, or being able to kind of alert on trend differentiating. Some good stuff. And so I just love to see this. Absolutely love to see this. The name is the Primegen. Unlike unsubscribe, report, DMCA, call my mom, do it all. You got it. A Jen.